Raw electricity, in its purest, untamed form, is a violently unstable and fundamentally unpredictable force of nature that naturally resists human control. To build the modern grid, the conversation almost always begins with Thomas Edison and usually ends with his rival, Nikola Tesla, who provided Westinghouse's patents. However, the specific technical problem that prevented electricity from spreading was solved by Wiilliam Stanley Jr., a man whose name is almost entirely missing from the historical record. Modern power's development was decided by an engineer working quietly in a small Massachusetts town, building the physical hardware that made widespread electricity functionally possible. In the late 1880s, Thomas Edison's direct current, or DC, system faced a massive geographical flaw. It could not travel far. A DC power plant could only push electricity about a mile. To power a city, you had to build generators every few blocks. Zooming out, the limitation is obvious. Urban centers had light, but the immense expanse of rural America remained entirely in darkness. George Westinghouse proposed an alternative, alternating current, or AC. This system was theoretically capable of traveling vast distances. But AC came with a specific logistical hurdle. To push power over miles of wire, the voltage had to be cranked to dangerous levels. To use that power in a home, the voltage had to be lowered. At the time, no one had built a reliable device to perform that conversion. Without a mechanism to safely step down high voltage, alternating current remained a dangerous theoretical concept. The expansion of the electrical grid was at a standstill. In 1885, Wiilliam Stanley Jr. retreated to Great Barrington, Massachusetts, to solve this specific bottleneck. His objective was to redesign the transformer, a device used to increase or decrease the voltage of alternating current. Existing transformer designs were inefficient and prone to overheating during continuous use. This cross-section shows Stanley's breakthrough, the closed iron core transformer. Instead of leaking energy into the air, the magnetic field transfers efficiently through a continuous metallic loop. This allowed massive, high-voltage energy to enter and exit as a low-voltage residential line. By closing the magnetic loop, Stanley reduced energy loss to a negligible amount. The physical barrier to long-distance power was removed. Stanley engineered the first iteration of a transformer robust enough to survive the constant, heavy demands of a functional power grid. By March 1886, Stanley was ready to test his prototype system in Great Barrington. Stanley integrated a generator, high-voltage transmission lines, and multiple transformers into the world's first comprehensive AC distribution system. When he activated the new power system, the generator pushed 500 volts down the street. The transformers lowered it to 100 volts, and incandescent bulbs flickered to life inside local storefronts. This test proved that electricity could be generated at a central plant and then distributed safely to buildings located miles away. The success in Great Barrington demonstrated that electricity could function as a scalable utility rather than a localized luxury for city blocks. Stanley's functional transformer gave Westinghouse the tangible hardware required to win the debate against Thomas Edison's DC system. Because power could now travel, factories no longer had to be located next to power plants. Industrial manufacturing began to expand across the region. This decoupling allowed engineers to build massive regional power stations. They could now harness immense natural resources, like the rushing waters of Niagara Falls, to power cities located hundreds of miles away. Supplied with affordable power from distant generators, 19th-century cities grew in size, density, and vertical height. The transition to the modern electrical system was enabled by Stanley's superior, scalable hardware. The isolated one-mile grids of the 1880s are fundamentally different from the interconnected infrastructure we rely on today. The continent-spanning webs of light visible from space are the direct result of the 1886 experiment in Massachusetts. Despite his foundational contribution to this global network, Wiilliam Stanley Jr. is rarely discussed. Stanley was a quiet, solutions-driven engineer, standing in contrast to the public personas and self-promotion of figures like Edison. While the names of promoters fill history books, the massive physical infrastructure that powers our modern world is built entirely on the solutions of engineers like Stanley.
Thank you for watching. Please like and subscribe. It really helps us.